Pille ma'am, am I audible?
Sir, you are audible, sir.
Okay. Let me try to share the screen. Whether the screen is visible?
Yes, it is.
Okay. You see the numerical there displayed?
Yeah, numerical it is visible.
Okay. So welcome, dear friends. We will be solving two numericals today. That is the plan of today's lecture. So I want you to have your notebooks with you and copy down this numerical. So read out the numerical, and you are expected to copy down this numerical, and then we will be solving this. I want you to copy it down because then I would be rubbing off this numerical, and then you might then face some problem with the data, right? So let me read this numerical. This is about the concepts which you have already learned in the earlier classes. This numerical is to test your understanding of, or rather improve your understanding of the entropy change issues. Okay. So we would be calculating the entropy change in this numerical for three things. That is, one is for the copper block, other is for the water, and third is the total entropy change of the universe during the process. These three entropy change calculations we will be doing, and then based on those calculations we would be deriving some insights about the actual process which is happening here. Okay. So let me read out numerical for you. It is already displayed on the board, but in case you're not able to see it clearly, I would be reading it out. Okay. So it is given that there is a copper block of 30 kgs of weight. Copper block of 30 kgs of weight, and that copper block is at a temperature of 95 degrees centigrade. Let me check this. Okay. 95 degrees centigrade, and it is that copper block which is at 95 degrees centigrade, 95 degrees centigrade, is dropped. It is dropped in 30 liters of water. It is dropped in 30 liters of water, and that water is at 24 degrees centigrade. That water is at 24 degree centigrade. So we need to assume this heat transfer which is happening here as a perfect heat transfer. So assume the heat transfer happening as a perfect heat transfer, and neglect all the losses which are happening to the surroundings. By surroundings we mean the surrounding of copper block and water. Okay, copper block and water. So in this heat transfer, assume that there is no heat loss to the surroundings. So what you are required to find is the following. One is you need to find the final equilibrium temperature. First thing you need to find is the final equilibrium temperature reached for water and for the copper block. Reached for water and the copper block. So you need to find the final equilibrium temperature reached for water and the copper block. This is the first part. The second part of the question is you need to find the entropy change of the copper block. You need to find the entropy change of water, and you need to find the entropy change of the universe associated during this heat transfer interaction. So you need to find the entropy change of copper block, entropy change of water, and the entropy change of the universe when this process of heat transfer is happening, right? And the third part of the question is you need to comment on whether this process is irreversible or not. Okay, and you need to justify your answer. You need to justify your answer. Okay, so these are the three things you are required to determine for this numerical. So try solving them. I will give you 2 to 3 minutes. Okay, and if you are able to come up with the answer, put your answers in the questions column along with your name, roll number, and division. Okay, right? So copy it down and try to solve this. We'll discuss the solution. Don't worry though, if you are not able to solve it, we will be discussing the solution. Okay. So whether you have copied down the question, please tell yes if you have copied down the question so that I can rub the board. Okay. If you have copied down the question, you say yes so that I can erase the board. Okay. Saurabh is saying yes. Mohan, Atharva, Vedant, they are copied down. Akanksha, Darshan, Neha, Tejas. Okay. So it appears that you have copied it down and I can drop down the question. Alright. So let me erase this question now. Okay. So I'm erasing this question now. Okay. So let me just represent this question. So there is a container, let us say. There is a container, let us say. This container, there is a container, and this container has water in it. This container has water in it. Okay, so there is a water in it, and this water is at 24 degree centigrade. 24 degree centigrade. Okay, and what is happening is there is a you are dropping a copper block. Okay, so this copper block, let us say this is a copper block of mass something. That mass is given to be let us say yeah, it's 30 kgs. This is dropped in this water, and this copper block is at a temperature of 95 degree centigrade. Okay, 95 degree centigrade. So this copper block is, it was earlier here, and this copper block is dropped. Okay, so we are dropping this, and that copper block is now immersed in water, and this everything. Okay, this you are assuming that this everything, this is an isolated system. This is a isolated system, meaning that there is no interaction of this system with the universe. Okay, so and this heat transfer which is happening is an ideal heat transfer. There is no loss to the surroundings. Okay, so this is the question, and first thing is you are required to find the temperature of final temperature of copper block, final temperature of copper block, and final temperature of water. So if you have calculated, some of you, tell me the answer. If you have calculated this, you tell me the answer. Okay. Okay, Kunal has got some answer. Kunal has got some answer. Okay, Sushant has also got some answer. Sushant and Kunal, they have got the answer. Anybody else who has got the answer apart from Kunal and Sushant? Okay, so both Kunal and Sushant, they have answered it correctly, and it is very simple actually. It is what is you need to figure out the energy balance. Okay, so the energy balance is what? The energy balance is that energy which is lost, energy lost by copper block is equal to the energy gained by water. Energy gained by water. Okay, energy lost by copper block is the energy gained by water. Okay. Now, what is the energy which is lost by copper block? So, the copper block loses the energy equal to mass of the copper block, Cp of the copper block, specific heat of the copper block, into the final temperature, that is the initial temperature of the copper block, because the copper block is cooling. Copper block is cooling 95 degrees centigrade. Okay, let me rub the unit here. So 95, yeah. Okay, so 95 minus the equilibrium temperature, final temperature. Okay, TE. TE means obviously the copper block, which is at a 95 degree centigrade, 95 degree centigrade, would have a drop in its temperature and it will reach the equilibrium temperature. Okay, equilibrium temperature, that is TE. TE. So that TE is the temperature of equilibrium, and the heat gained by water. Heat gained by water is what? Is water would experience a increase in the temperature. So mass of the water into specific heat of the water into the increase in temperature. So what would be the temperature of the water finally? That would be the equilibrium temperature, because the copper block and water would reach a equilibrium temperature. And what was its temperature earlier? The initial temperature was 24 degrees centigrade. So solving this equation, that is M of copper, Cp of copper into 95 minus Te is equal to mass of water into Cp of water Te minus 24. If you solve this, you are given the water is 30. What is the mass of water? It is 30 liters. Means 30 liters means 30 kgs. 30 liters means 30 kgs of water. Cp of water, you know, that is 4.187. 4.187 is the Cp of water. Okay. Mass of the copper is given as 30 kgs, and the specific heat of copper is given to be 0.386. 0.386. So if you put the value, substitute this value around 30 degrees centigrade, which is nothing but 3. Kunal, they have got it correct. All right. So this was the first part of the question. Okay. I hope now it is clear to all. Whether this first part of the question is clear to all of you. If it is clear, say yes. First part of the question is clear to you. First part of the yes or no? Okay. Thank you, Yuraj, Samir. Right. Now we'll move to the second part of the question. Let me rub this. Now, let me ask one question. What would happen to the entropy of the copper block? Whether it would increase or decrease? You have to answer this question. What will happen to the entropy of the copper block? Whether it would increase or decrease? What would happen to the entropy of the copper block? Whether it would increase or decrease? Tell me this. Answer this question. What would happen to, okay, Mayur is saying that the entropy of the copper block would decrease. What would happen to the entropy of the copper block? Whether it would increase or decrease? Kunal is saying it would decrease. Tejas is saying it would decrease. Garge is saying it would decrease. Anyone who is saying that it would increase? Atharva is saying it would decrease. Akanksha also says that it would decrease. So the answer is the entropy of the copper block would decrease. So calculate the entropy change of copper block now. Entropy of the copper block would decrease. That is, the final entropy of the copper block would be less than the initial entropy of the copper block, and the entropy change would be negative. So you calculate the entropy change of the copper block now. For calculating the entropy change of the copper block, the hint is entropy change of the copper block. Entropy change of the copper block is equal to integral of del q by t. Integral of del q by t. Okay. From the initial state. What is the initial state of the copper block? It is, initial state is how much? It is 95. 95, and finally 95 plus 273. 95 plus 273, and the final temperature of the copper block is 30 plus 273. 30 plus 273. Okay. So you calculate the entropy change of the copper block now. You have to solve this integral. So solving this, let me write down integral of m cp dt by t. Okay, m cp dt by t from 95 plus 273 is 368, and this is 303. So this becomes mcp ln t2 by t1 which is equal to m is how much? M is 30. Cp is how much? Cp is 0.386, and log to the base e, that is ln 303 upon 368. Okay, so calculate this value and tell me the answer. Tell me the answer. That kilojoules per Kelvin would be the entropy change of the copper block. So you calculate and tell me the answer. Okay, Sushant has already calculated. Anybody else who has calculated this? Kunal has calculated. Atharva has calculated. Pranav has calculated this. Neha has got the answer. Mayur Sadavarte. Just recheck your calculation, Mayur. You are slightly off the mark, Mayur. Tejas has got it correct. Okay, so the correct answer is minus, you can just, you have to use your calculators for this, minus 2.25 kilojoules per Kelvin, okay, minus 252. If I want to go slightly ahead, so it is minus 2.2506, okay, kilojoules per Kelvin. So that is the negative sign. Now, why do you find that the entropy of the copper block is decreasing? What is the reason? What is the reason that the entropy of the copper block is decreasing? Why is the entropy of the copper block decreasing here? Yeah, Sairaj is correct. Because I had told you that along with the heat flows the entropy. Along with the heat flows the entropy. So the heat is being rejected by the copper block. Hence its entropy would decrease. Okay. And now you have to calculate. Now you have to calculate that the entropy change of water. So you calculate using the similar method now. Calculate the entropy change of water. Entropy change of water. Calculate the entropy change of water now and tell me the answer. Okay. Calculate the entropy change of water and tell me the answer. So the entropy change of water, if I want to write it somewhere here, so let me use another pen. So entropy, I am using a blue pen for that. Entropy change of water would be integral of del q by t, okay, del q by t from initial temperature is 24 plus 273 Kelvin, okay, and the final temperature the water reaches is 30 degrees centigrade. 30 degrees centigrade. So 30 plus 273. 30 plus 273. Okay. So this again is integral of mCp dt upon t from, this is 297 and this is 303, which is mCp mCpln, it is 303 upon 297, where now in this case Cp of water here, 4.187, and the mass of water is 30 kgs. 30 liters means 30 kgs. Okay, so that will give you an answer, and you'll find that that answer is positive, and you can write down that answer. Yeah, Akanksha has got this correct. The answer is Sairaj is correct. Neha, Kunal, Yuraj has also got it correct. Okay, so you will find that a very interesting thing you will find is Sushant has got it correct. You see here that a very interesting observation you can find here, that this is 2.5123 kilojoules per Kelvin. Okay. So now you need to figure out what is the entropy change of the universe, okay, in this interaction. So entropy change of the universe, look at this, okay, there is an interaction here. So the entropy is, you will find that the entropy is not conserved. Are you getting the point? The entropy is not conserved in this case. What you are finding is in this interaction, what is happening? Whether the entropy is equal to entropy increase, whether the entropy decrease is equal to entropy increase. What is so interesting about it? you'll find that there is an entropy decrease of the copper because heat is lost by copper. You'll find that there is an entropy increase of water because heat is gained by water. Okay, and you'll find that there is no heat loss. There is no heat loss. Okay, in spite of that, you will find that the entropy change of copper, okay, the decrease of entropy of copper is less than the increase in entropy of water. Are you getting this? This is a very interesting observation. You just think over it and try to figure out what it tells you. Try to figure out what it tells you. Okay, you'll find that the entropy decrease of copper is less than, okay, and what could be the reason for that? What could be the reason for that? To see that it is an ideal case of heat transfer. There is no heat loss, absolutely no heat loss, okay, to the surroundings. And in spite of that, okay, and you have figured out that whatever is the energy lost by copper block is the energy gained by water. Okay, and in spite of such an ideal case, ideal scenario, what you are finding is the entropy change of copper is less, whereas the entropy change of water is more. That is, the total entropy change is in fact positive. Okay, the entropy change of this isolated system is positive. So what does it tell you? What does it tell you? Can anybody answer this? What does it tell you? It tells you that the process is irreversible. What it tells you is that the process is irreversible. Okay, and that difference, yeah, Vedant is correct. That difference, that is the difference between the entropy change of copper and the addition of entropy change of copper and addition of entropy change of water, that difference which will come as, if you add this two, what is the value you get if you add the two? Tell me the value of adding the two. It would be minus, which is how much? Which is how much? Is how much? 506 plus 2.5123. That value is 2617. If you add, yeah, Sairaj, it is correct. There is an increase in the entropy of the isolated system, meaning that this energy interaction, which is involving zero loss, this energy interaction, reversible energy, is quantified by the number, positive number, which is 0.2617. Okay, so that is the beauty of the concept of entropy. Okay, so what does entropy, why are we studying entropy? We are studying entropy change because that entropy change helps you to quantify the irreversibility. So the concepts of reversibility and irreversibility which we are studying from a conceptual angle. Okay, that is from the quality angle. Now we are in a position to quantify those. We are now able to put them in numbers. Okay, so this number, what does this number tell you? 0.2617 kilojoule per Kelvin. That number, positive number, 0.2617 kilojoule per Kelvin, tells us that this energy interaction, that is this heat transfer from the copper block to the water, this process is an irreversible process. This process is an irreversible process. I hope you understood this. If you understood this, say yes. If you understood this, say yes, and then I can move to the next problem. If you want me to repeat, say you repeat. If you understood this, say yes, and we'll move to the next problem. Okay, Dheeraj has understood. Tejas understood. Akanksha, Gargi. Okay, so should I move to the next problem now? Okay, Sharvari, Vaibhav Deshmukh, Yash More, Ganesh. Okay, all right. So let me go to the next problem now. Uh, I'm rubbing this. Thank you, Deepak. I'll be rubbing this. Abhijit. Okay. All right. I'm assuming that all of you who are attentive and who are solving this along with me in your notebooks, they understood this. So please, for the next problem also, if you had no notebooks, ensure that you have the notebooks with you and copy down the next problem. I am dictating the problem, and also I will be writing down the problem. Okay. So I'm dictating the problem and I'm also writing down the problem. Take down the problem. This also is a problem of copper block. This also is a problem of copper block, but with certain difference. Okay. Okay. Now, a copper block of mass 1 kg. The question is, yeah, one more example I'm taking, Mayur, but with slight difference. Okay. So a copper block of mass 1 kg, copper block of mass 1 kg. Both these problems which I am solving, they are university problems. Okay, so you might find this problem in some textbook also. Is immersed copper block of mass 5 kg and at 500 Kelvin is immersed difference. If you compare this problem with the earlier problem, you will notice that this is the difference. Okay, and how it is different, I will tell you. Take at Kelvin till it reaches the equilibrium temperature. It reaches till it reaches equilibrium temperature. Okay, equilibrium temperature, right? So this is the question. Now, you are required. It is given that the Cp of the copper block is 0.386, similar to your earlier problem, and Cp of water, you can assume, even if it is not given, you must know this value, 4.187 kilojoules per kg Kelvin. Okay. So what you are required find is you are required to find one, the heat transferred, Second, you are required to find the entropy change of copper block, and third is the entropy change of lake. Entropy change of the lake. Okay, and the overall entropy change and the entropy change of universe. Entropy change of universe. Okay. 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 Heat transport, entropy change of copper block, entropy change of lake, and entropy change of universe. Okay. Okay. Some students are quite fast, but I will be moving slowly. First thing is you need to calculate the otherwise got it correct entropy change of Vedanta got it correct. Atharva and Vedanta got it correct. See, look at this. What is the difference here? The difference is the following. Okay. So the difference is the following. This is the lake. Okay. Now in that earlier case, it was a known quantity of water and it was a small quantity of water. Okay. In this case, what you are having is a lake, and in this lake now the copper block is falling. Okay, the copper block is immersed. Right now, what will happen to the temperature of copper block? What will happen to the temperature of copper block? Answer this question. What will happen to the temperature of copper block would what will happen to the temperature of copper block? It will decrease, right? Pranav, Sairaj, it will decrease. So the temperature of copper block would decrease. What will happen to the temperature what would happen? Yeah, Gargi, correct. What would happen to the temperature of a lake? So temperature of copper block would decrease. What would happen to the temperature of lake? Temperature of lake. What would happen to the temperature of lake? It would increase. Gargi is saying it would increase. What would happen to the temperature of lake? Vedant, Gargi, they are saying it would increase. Any other answer? Neha is saying that it would remain constant, and Mayur is saying that it would slightly increase. So the correct answer is what Neha has said. It would remain constant. Okay, it would remain constant. And why is that so? Because as Neha has understood this would act as a reservoir. Okay, this would act as a reservoir, and because it would act as a reservoir, you see that lake is an enormous source. Sorry, it has an enormous quantity of water, and you are transferring very negligibly small amount of heat to it. So we can, and it would be a very good assumption, we can assume that the lake would behave as a sink. The lake would behave as a thermal reservoir. It would behave as a sink, and we know that a sink is a thermal reservoir whose temperature remains unaltered when you are transferring the heat to it. So in this case of heat transfer, considering the quantities of heat transfer which you are talking about, okay, we can assume the temperature of the lake to be constant, and that is the correct assumption. We can assume the lake to be at a constant temperature. Okay. So then your calculations become now very simple. Okay. It means now your entropy of entropy change of copper block, you need to calculate as like this, as we had done it earlier, that is integral of mCp dt upon t. Okay. However, the entropy change of the lake, because your temperature is constant, in this case, so if you solve the integral, it will be q upon t. And what would happen to the entropy of the lake? The question is, what would happen to the entropy of the lake? Whether it will remain constant? What would happen to the entropy of the lake? What would happen to the entropy of the lake? What would happen to the entropy of the lake? Gautam is saying the entropy of the lake would remain constant, which is not correct. The entropy of the lake, no, Yuraj, it is not correct, Yuraj. Atharva is right, Vedant is right. The entropy of the lake would increase. The temperature remains constant, but the entropy of the lake would increase. The entropy of the copper block would decrease. The temperature of the lake would remain constant. Please note this. The temperature of the lake would remain constant. However, the entropy of would the entropy of the lake increase? Why would the entropy of the lake increase in spite of the fact that the temperature remains constant? Why would the entropy of the lake increase in spite of the fact that the temperature of the lake remains constant? Why would the entropy of the lake increase? Yeah, correct. Gautam is correct. The entropy of the lake would increase because heat flows into the lake. So heat flows into the lake. So along with the heat flows the entropy. Hence the entropy of the lake would increase and the entropy of the copper block would decrease, because from the copper block, because copper block is being cooled, so there is a heat rejection from the copper block, its entropy would decrease, and there is a heat gain by the lake, its entropy would increase. Okay, so now solve this. So you need to first find out q. So how do you find q? Q is equal to mass of copper block, Cp of copper block And what would happen to the copper block? What would be the temperature of the copper block finally? What would be the temperature of the copper block? The copper block was at a temperature of 500 Kelvin. 500 Kelvin. The lake is at a temperature of 300 Kelvin. So when you are immersing a small block of 1 kg, 1 kg copper block, when you are immersing that copper block of 1 kg in this water, the temperature, the final temperature of the copper block would be 300 Kelvin. It means that the copper block would come in equilibrium. Okay, it will come in equilibrium with the lake temperature. It will come in equilibrium with the lake temperature. So this you have to understand it clearly, that the copper block was at 500 Kelvin. When it cools, its temperature becomes 300 Kelvin. Okay, the lake initially was at 300 Kelvin. Even after the copper block is immersed in the lake, the temperature of the lake would not change. It would remain 300 Kelvin. However, the lake would gain the heat. How much would be the heat gained by the lake? So the heat gained by the lake would be equal to the heat lost by the copper. Heat gained by the lake would be the heat lost by the copper. And how much is the heat transferred by copper to the lake? Heat transferred by copper to the lake would be mass of the copper, Cp of the copper, and temperature difference, 500 minus 300. So that value becomes, mass of the copper is 1 kg. Cp of the copper is known to you, that is Cp. 500 minus 300, that comes to 77.2 kilojoule. Okay, so this is the heat transferred by the copper. Okay, heat transferred by the copper. So this 77.2 is the heat which is lost by copper, which is equal to the heat gained by lake. So this has to be positive. Why is this positive? Because heat is gained by the lake. So that value would be 77.2 upon temperature of the lake is 300. So that becomes the entropy change of the lake. That is 0.2573 kilojoules per Kelvin. So this is the entropy change of the lake. These calculations are similar to your earlier calculations. The entropy change of the copper block would be negative, and that if you substitute the values, you'll get as 1.1972. Okay, kilojoules per Kelvin. You can substitute the value of m as 1 kg, and the temperature change happening from what was the initial temperature? The initial temperature was 500 Kelvin, and the limits are 500 Kelvin to 300 Kelvin. Okay, so if you solve this integral from 500 Kelvin to 300 Kelvin, mCp dt upon T, where Cp of the copper block is known, mass of the copper block is known. If you put this value, you will get a negative value, and the negative value why you will get, that I have already explained to you. And if you add this two, you will get some positive value. That positive value is the quantification of the irreversibility or entropy generation in the universe because of the irreversible heat transfer. Because of the irreversible heat transfer. I hope it is clear to you. I hope it is clear to you. Yeah, Veda, Akanksha, your answers are correct. Sairaj, your copper calculations is correct. Gargi, what is 200 Kelvin you are written? Vedant, Yes, you're right. You'll find that Vedant, there is a positive value of entropy change of the universe, and the reason is because the process of heat transfer is irreversible. The process of heat transfer is irreversible. Okay. So the values which Vedant has got, they are correct. Yuvraj, you recalculate your value. Yuvraj Singh, you recalculate your values and put down those values. Anybody who has not understood this, anybody, you can tell me if you have not understood this. I will repeat it if you have not understood this. Anybody who has not understood this problem, you can say, I can repeat it. Okay, no problem. If you understood this, then it is okay. Anybody who has not understood this and you want me to repeat, I hope it is clear. The problem, both the types of problems are clear to you. So, need to understand that why are we calculating this? We are calculating this to understand how much irreversible the process is. Okay, we are trying to figure out how much irreversible the process is. We know that because there is a finite temperature difference between the copper block and the lake. There is a finite temperature difference between the copper block and the lake. That finite temperature difference is responsible for irreversibility. Okay, but how much is it irreversible? That we have quantified by calculating the entropy change of the universe, that is the entropy generation in the universe, right, as a summation of entropy change of the copper block and the entropy change of the lake. And this, you must understand that this positive value you are getting in spite of the fact that there is no energy loss. There is no energy loss. So energy is conserved. Energy is conserved. However, the entropy has increased. Entropy of the universe has increased. And why is that increased? Why is the entropy of the universe increased? The energy is conserved, but the entropy has increased. Why has the entropy increased? Why has the entropy of the universe increased in this interaction? Any answers? Why has the entropy increased? The answer is the entropy of the universe has increased because of irreversible heat transfer. The entropy of the universe has increased because of irreversible heat transfer. Okay. All right. Thank you very much for being online. I hope that your concepts of irreversible heat transfer and how to solve numericals involving irreversible heat transfers is they are clear to you. Okay, we will solve few more numericals of different type in the next class. Okay, thanks for joining. Have a good day.
Thank you, sir.
Okay.